Hey everyone, here I'm going to do a CFD problem using the Ansys Fluent and create our pressure, velocity and turbulence counters in the required geometry. So what is CFD? So CFD is a branch of the fluid mechanics that uses numerical algorithms and computer simulations to analyze how the fluids behave when they flow over or through the objects. So here the CFD helps to predict the velocity, pressure and the temperature counters. It helps to visualize the flow patterns and analyze the heat transfer and the turbulence. So CFD helps to convert the governing physical laws of the fluid flow into the mathematical equations. So what are the basic fundamentals of the CFD? The CFD is based on three main fundamentals: governing equations on physics. This helps in the continuity equations, Navier-Stokes equations, and the energy equations for the heat and temperature effects. And for the mathematics, numerics, we have the discretization method. The physical geometry is divided into small cells called a mesh, and the equations are solved numerically at each cell. So we have common numerical methods are finite volume method, finite element method, and finite difference method. So here the solver and post-processing is there for the computation and visualization. The solver calculates the flow variables and the post-processing converts results into velocity counters, pressure plots, temperature maps, and the streamlines. So what is the main importance of the CFD? That it reduces the cost of physical experiments, saves the times in product development, and improves the design accuracy, enhances the safety in the aircraft explosion, and enables innovation for the high performance and electric vehicle thermal systems. So what are the main applications that we can use CFD in the real life? So we can use the CFD in aerodynamic engineering. That means like in the sector of automotive engineering, aerospace engineering, mechanical and industrial engineering, biomedical engineering, environmental and chemical engineering as well. Hello everyone. Today I'm going to do my analysis for the catalytic converter. So I'm using the Ansys Fluent. So I'm now here, I'm making the design in a design modeler. So here I'm making the dimensions, taking all the units in millimeter and making the diagram in z coordinates, z directions. So I'm making the circle over here. So now the circle is having the dimensions of 40 mm. So I'm making the sketch now. So first is the circle, and then I'm making the extrusion of this circle of 100 mm. Added the frozen, then generate. So the extruding is done. So now I'm taking the next sketch and making the circle again. Taking the circle, pointing it out at the z0 coordinates. Sorry. Making at the center. So now making the circle, having the dimensions of 100 mm. And then now giving the extrusion, so extruding the part as adding the material as a frozen and giving the depth of 100 mm, that is reversed. Now generate. So now the required half part of my geometry has been done for the catalytic converter. So now I'm taking the new plane and shifting the coordinates to the center. Turn plane, taking the coordinates, selecting as 100, it comes to the front, so taking minus 100. So it'll be at the center of my sketch. So now click the generate. Now I'm mirroring the image. Let's create with the body transformation and then mirror. Select the body that I want to mirror, apply, and then the plane. Then generate. So this is my required diagram. So I need to make this as a one body. So use the create boolean operation. Use the boolean and select the body and unite the body. Apply and generate. So this is the required geometry. Now I'm making the chamfer design. Use the chamfer and click at the corners and then apply, making the dimension as 30 mm. I'm sorry. Then generate. So this is my final design of the catalytic converter that I want to get analysis using the Ansys Fluent. So generate. So if I want, I can change the three bodies into one part and three bodies like this, and then generate. So you have one part and three bodies. So now I'm gonna save my geometry. So here what I'm about to do is, by making the geometry, I'm going to check the pressure counters, velocity counters, and the turbulence counters. That means the inlet pressures, velocity, and turbulent kinetic energy changes from inlet to outlet. So we are going to see all the figures and diagrams. So now I'm saving the process in the desktop. And this is a catalytic converter. So catalytic converter is the main part of the vehicle dynamics. So now I'm going to open the mesh from my geometry. So it will take a little bit time. So for decreasing the efficiency of the vehicle engine, our catalytic converter and the exhaust manifold plays an important role. So now I'm opening the meshing, giving the sizing for the meshings at the corners, and then apply the geometry and give the type as a number of divisions. So I'm here taking the number of divisions 150, otherwise 300 depending, and I'm making the mesh size at 0.001 meter. So I have given the nodes and elements as this one, and I have named the selection part. This is inlet, outlet, porous media, inlet, and the outlet part. This is my required mesh. Then I'm saving the mesh and opening the solution part. Here I'm using the model as SST key omega model, having the key omega two equations, and SST. Click OK. So then I'm using the fluid here as a nitrogen and air. So probably nitrogen will be the best. That will be going off from the engine, and taking the body as the aluminum. So checking the cell joint condition, inlet, outlet section, and the porous media. So here all the sections should have the components that is entering should be fluid, that is nitrogen. So this is the boundary equation for mine, that is the inlet. So velocity inlet, I have taken the velocity inlet as 20 meter per second, and intensity and viscosity of the turbulence, and the outlet as the same as the inlet, but not the velocity, but I'm here taking as the intensity and viscosity ratio as the same. Then I'm checking out the residuals. The method is the same, coupled one, second order upwind. Checking the monitor residuals. I'm taking the continuity x velocity, y velocity, jet velocity as 1 into 10 to the power minus 5. Q omega has given 0.001. So this is my required mass. So after the calculation is completed, after the initialization, so the required, we can see that the calculation is complete. Now I'm going to see the required integral part for the pressure, velocity, and the turbulence. So I'm going to surface integral, taking the area of the inlet outlet sections. So we need to change the surface. This one is the area covered by the inlet outlet sections. So now here I'm checking out the surface integral again for the pressures compared. We can see the inlet pressure, that is 4.9 Pascal. Outlet sections we have not given, and the inlet sections is the same. The net pressure is 53. So in this way we can calculate for the velocity. Select the compute. So this is the required velocity of the inlet, outlet. So the net velocity is 0.05 meter per second. So in this way we can check out the turbulence. Select the compute. This is the required turbulence at the inlet, outlet, inlet sections, outlet sections, so that the net turbulence is this much. So in this way we can check out all the surface integrals. So now I'm checking out the results after the completion of the solutions. So opening the solutions here. Now I'm going to check the required figures with all the counters at the pressures, velocity. Checking different counters using the plates. So I'm using the plane one. Sorry. So I'm using the circular radius of 100 mm. So select jet minus 100, then apply. So you can see the one plate. Otherwise you can change the type. Change the type to none. So you can select the plane 1 is hidden, so the plane 1, you can see now the circles that has been adjusted. So I'm taking the plane 2 on the same axis, having the jet as -30 and the type as a circular, taking 100 mm. So I'm taking one plate at the center, one at the one corner at -30 mm z-axis, and I'm taking another plane now that is plane 3 in the xy plane, z as -170 mm. That is the third plate. Circular, 100 mm radius. Now you can apply. So here comes the third plate. Now here I can see the counters. Taking the counter 1, selecting the locations as the inlet, a location as a plane 1, sorry. So giving the pressures as a variable and the range local of the counters 100. So it takes a little bit while. So this is the required pressure counters in the axis of the plate at the mid. So simultaneously you can check the counter 2, take the location as a plane 2, variable is the same, pressure, range local, and you can apply 100 counters. And similarly for the same process for counter 3, select the plane 3, counters 100, and the range local, and then apply. So these are the 3 plates that is showing the pressure counters. Just similarly, let's see the same application, changing the variable for the velocity and applying it simultaneously for counter 1, 2, and 3 respectively, and change the range to global. So this one's for counter 2, global, apply. Now for the counter 1, velocity, global, apply. So this is the required velocity counters we have. Now I'm taking counter 4, taking location as the inlet, variable as a velocity, and the range global. Having the counters of the 100, take apply. So you can see the inlet counters of the velocity, and again taking counter 5, location outlet, same variable as velocity, range global, then apply. Counters of 100, apply. You can see the outlet. So I'm deselecting the plane 1, 2, and 3. Now I'm applying the same for saying the pressure variables. So you can change different variables and see whatever you want for the different counters. I is a pressure, velocity. So taking to pressures, so you can see there is a decrease in pressure from red to blue. So I'm taking the plane 4, taking the JetX plane method, y equals 0, apply. So you can see the flat surface as a center axis. So I'm checking out all the counters. So this is the required plate for the plane 4. I'm taking counter 6 with the location as a plane 4, variable as pressure, global counters as 100. Unmark the plane 4. So these are the required pressure counters. Now I'm changing the variable to velocity and see what happens to the diagram. So these are my required velocity counters. So I'm unmarking my wireframe and this is the required. So now I'm inserting the velocity vector. Insert the vector. So now I'm applying the location as a plane 4. Sorry. So I'm taking the counters now as a counter 6. I'm unmarking the counter 6, changing the symbol. You can see the flow of the movement of the velocity. So in the diagram, after changing the symbols here, you can check out with various. So I'm taking the arrow 2D and the size 1.85. Apply. So this is the required diagram for the velocity vector. So lastly, I'm going to check this streamline starting from inlet forward, apply. So we can see the streamline animations which represent the heat flux movement from inlet to the outlet. So unmark the velocity vectors, 100 points. Now you can see the required, select the streamline and then play. Select the slowness, play. So now you can see the heat flux movement from inlet to the outlet and the required streamline diagram. So this is the velocity streamline flow of the heat flux. So now moving forward, I'm taking the another. So this one's for the same process for the animations. Now I'm taking the new counters. It's counter 7, having the number of counters from Porous Media. Another one, counter 8 from one wall inlet sections. So this is from the wall porous zone. Take the counters as 100, then apply. Sorry. Now taking the counter 8 from the wall inlet sections, counters as 100, then apply. So you can see the change in the colors, rainbow colors, patterns showing the pressure counters. Now taking the counter 9 from the wall outlet sections, counters as 100, so you can unmark the velocity vector flow if you want the clean plane result. So I'm saying this again, required for the velocity. It is showing the changes, but it is being changed inwards only, not at the outwards. So thoroughly you can change all the activities with the pressure velocity depending upon the situation that you want. Now on marking this streamline, this is the required figure. That is the movement of nitrogen in the catalytic converter. So I can change and play with the colors and stuffs. So here I'm changing the render to switching off the lighting and the counters so that it is showing the 3D structure. So if you want the images, you can save the images in the desktop and checking the color gradient using the geometry. Change to color map and the rainbow, fluent rainbow color. You can do whatever you like which is suitable for you and save the image. So from this, what we can see is, so this one I took in the plane surface of the catalytic converter here. I noticed a small change due to the design workflow. There is change in pressure, velocity and the turbulence. So simultaneously I want to check and modify the diagrams by making the barrier at the between. So in the same figure I process the barrier filter and made the honeycomb structures, and here I made the barrier, that is one circle in between, and here I changed the edge sizing. So this is my required mesh. The same outlet section, inlet section, power zone, inlet outlet, and now I'm making the filter barrier in the between. So number of divisions I took for the first 150 depending on the characteristics. You can play with the sizing, and then after I move forward to the solution after finishing up my meshing. Here the meshing nodes was much more than million. That's why you need to have a good version of the Ansys Fluent. The student version is not capable of doing the good mesh more than 1 million. So this is the required solution geometry with the barrier in the between. So I'm changing all the activities are same as before, just the geometry is being modified at the between, having the honeycomb structure. So let's check out the methods that I applied. The method is the same. The monitor residuals I applied, that's also the same. 1E2 bought in the power 5 is all the solution activities are the same. So checking out some integral part, if I can see any changes. So selecting after the completion of the solutions, checking out for the pressures, because the solutions may take almost like 1.5 or 3 hours. So checking out the integral part of the pressures here, you can compute. So it may take a little bit while. So the inlet 884, you can see, while inlet section is having this one, while outlet section having a minus pressure, and the wall pore stone. So net is 31,651.68 in Pascal 472. So I can check similarly to the velocity. So the net one is 0.05. You can see the inlet and the outlet velocities. So velocity decreases as it goes, as it is blocked by a barrier. So in our modern days, the barrier is there acting as a filter, so that the harmful gases are not ejected out from the catalytic converter to the atmosphere, which helps in the ecosystem. So in this way, you can check out for the turbulence. So moving forward, I'm checking out the same solution path like I did it earlier in the catalytic converter without the barrier in between. So here I can see I'm taking the same honeycomb structures. Now I'm giving the same distance circular plate as before. So I took the plain one, similar, taking the wireframe. The activities is same as all as before, taking the plain one, plain two, and then plane 3, the XY plane. And then changing the required pressure variables, velocity variables, same as before. So we have minimum minus 562.522 pascals and maximum 70.404 pascal. So you can play around with all the counters and the plane and show the result whatever you like. So now I'm changing it to velocity and checking it out. For the counters, apply. The minimum velocity ranges from, it depends in which plane you are taking, because different plane goes through different velocity. So you can see that with the change in the center barrier, there the outlet has been changed in the pressure, velocity, and the turbulence characteristics. So it ultimately, like, there is a change in efficiency of the vehicle due to it, because we can see that if the filter acts as a barrier there, which helps in the ecosystem to not pour out all the harmful gases towards the atmosphere. So in our modern practical way, we can think is that the filter and barrier may decrease the velocity to some extent, but it helps too in the ecosystem in ejecting out the harmful gases to the atmosphere. So here I'm now again taking the same plate at the center axis, and it's the same process as the beginning, taking the counters 1, counter 2, counter 3, plane 1, plane 2, plane 3, then changing the velocity, pressure characteristics, taking this out for the pressures. So now for the velocity, having the counters of 100. So you can play around and see the counter 4, counter 5. Having the inlet and the outlet, and play with it regarding the pressures and the velocity in it. So here also you need to insert the velocity vector. So this one's on. Here's the velocity gradient in counter 6. So now this one is for velocity, checking out the movement from the inlet to the outlet. Symbols, you can use arrow 2D. I'm taking 1.85 as size. Apply. So there is a flow of the movement of the gases. So now I'm checking out the streamlined body on marking the velocity vector. And with the streamline, you can see the same result as the before. There will be the movement of the heat flux from the inlet to the outlet. And you can see the required derived result. And again you can see the animation, how is the movement. This one is for the porous media zone, that's from counter 7. And we can see simultaneously from the counter 8 location Y inlet section and counter 9 outlet section. So this is the required 3D diagram, taking into consideration of the fluid rainbow color map in the geometry. So you can play with the required. So this is my second figure where I modified the geometry at the center to act as a barrier layer for the inlet, and checking out what are the pressure counters, velocity counters, and the turbulence kinetic energy at the outlet. So this is my required chart that I have taken out regarding for the pressures. This one's for velocity. This one's for turbulence kinetic energy. And this for mass flux flow rate. So now again, this is the third figure I'm taking. Here I want to check how the pressure, velocity and kinetic energy changes if there is a leakage at the corner or center of my catalytic converter. So now here I'm modifying the geometry by taking at the one side. I want to take the potholes, so I'm sketching the geometry here by changing the coordinates in the z directions so that I can draw the circle over there and see the leakage. So these leakages are the things that we can find in the real world applications. So that probably can happen due to the stones, or might be the catalytic converter that is being burned out, or something like there is impact of some stones or some things on the surface of the catalytic converter. So how it is affecting the engine performance. So I want to analyze that. So here I can analyze only the pressure, velocity, and turbulence kinetic energy. So I'm now here making one circle over there at the top right corner. So I'm making circle driven to the center, extruding the cut. So I'm taking one 15mm circle die. So now I'm extruding the cut. Again changing to 10. So I'm extruding the cut. Apply. Slice the material and then generate. And the add frozen material that was placed at the between. Here the sliced material is in a little bit different from the regular extrusion cut. So now I'm saving the geometry again. Now going for the mesh. I'm sorry. So that is the required leakage holes at the corners. So I'm now changing the mesh sizing. Same as before, taking the corners. Making the number of divisions as I'm taking here 150 or 300. Then the curvature as no, behavior as hard. This is applicable for all the three figures. Updating the sizing. So due to the hole in the geometry, the mesh division doesn't become uniform. So that I need to put the inflation layer at the circle point where there is a leakage. So I'm inserting other sizing method at the jumper part. So applying the sizing, number of divisions to 300, curvature no, and the behavior hard. Update. So I'm changing the mess. Now I need to put the inflation layer at the leakage point, that is at the extrude cut sliced material. So I'm sizing the leakage corners. Number of divisions is 100. No. Curvature part and behavior hard. Update. So in every app, taken the mesh as 0.001 meter. So there got some problem in the mesh, so I'm redoing it again. So doing the same process it again, taking the edge sizing, jump of part corners, apply, number of divisions 300. No. Curvature behavior hard. Generate the mesh. Then sizing for the leakage point. Number of divisions 100. Taking curvatures no. And the behavior hard. Generating the mesh. Inserting the inflation layer at the leakage point. Apply the boundary surface of the leakage point, and the inflation type. First layer thickness I have taken here. First layer has 120. Generating the mesh. Update. So the mesh might take a while because we got the bigger mesh. That's why. So if there is a problem in the layer thickness, there will not be the mesh. So you need to again check out the mesh properly. So I'm redoing the surface of the inflations layer, and you have the mesh like this. So it's a very good mesh, having the inflation layer at the center. So I'm taking first layer thickness. So I'm naming the part at the inlet section. Porous media, porous cylinder, outlet section, inlet, and we have two outlet. I'm taking out outlet 1 and outlet 2. So I'm saving the mesh, saving the project. So I'm opening this setup file, double precisions, having 4. So all the whole setup is all as before. So due to the leakage, practically what we can see is efficiency decreases due to the potholes at the cylinder in the catalytic converter. So this is the required diagram in the solution output. So I'm changing the model. You can, if you want to check the temperature gradient, so you can the energy equation you can on and off. Otherwise I have taken the model as SSD K epsilon omega. And the materials here I've used is nitrogen. You can add using the chemical formula, Fluent database. Check out the nitrogen from there. Then copy. So if you want, you can select another solid part. That I have taken is steel due to its low coefficient of thermal expansion and coefficient of thermal conductivity. Then I have changed the cells and condition of the inlet sections. We have to choose all the inlet, outlet, and the pore cylinder conditions, that the particles going inside and out, that should be the same particles. So you need to put the fluid as a nitrogen for all the part. Apply. Applying for the outlet section. Part solid should also be nitrogen. I'm sorry. Then you need to initialize. So after solution, you can see the required pressure, temperature, and turbulence change. So this is the inlet 366.3667.0818 and the net is 1470. So here you can see the pressure is being lost due to the leakage in the cylinder. And the velocity, I have sent the velocity inlet at 20. You can see 2 outlet is there, so it's decreasing from one outlet, and from the another outlet there is a more pressured velocity. The net is 25, so there is increase in velocity from this outlet cylinder, from the 2 outlet. And the turbulence is also will be more because there are 2 outlets. So the net turbulence will also increase and the engine will vibrate more in the practical applications. So in this way we can check out all the different counters in the solution itself, and this is the required plot of the pressure counters. You can see these same solutions that can be found through the solution methods by making all the blocks, but here we can check it out directly from here as well. And now I'm checking out for the velocity, save display. The velocity goes from the inside, that's why we cannot see that, but you can see the red. That means there is more velocity from the leakage point. And you can see the green means that is the average inlet and the outlet. Sorry. Turbulence. Save display. So in this way, we can check out all the required parameters in the Ansys Fluent. So in the real world application, due to the leakage, we can see that there is various effective in the engine, and the performance and the efficiency decreases. Thank you.